Welcome back. This is the Thermodynamics 2 homework solutions at the South Dakota School of Mines and Technology. We're on homework number 8, problem number 4. This is reaction equilibrium. Okay. And number 4 is straight out of Koretsky's textbook. It's 9.23 in the second edition. It says, consider the industrial production of cyclohexane by the gas phase hydrogenation of benzene, C6H6. Assume that this process is carried out by two reactors in series as shown below. Basically, in the picture, which I'm not going to draw because my eraser is having issues and I don't want to have to erase it, I got hydrogen combining with benzene. Hydrogen is in a 10-to-1 ratio. It's going into this reactor that's at a pretty high temperature and a fairly high pressure. And in the second reactor, I lower the temperature. Okay. Based on whatever comes out of the first reactor. Alright, so so I'm high pressure, high temperature, high pressure, and then I go to high temperature, same pressure. The feed ratio of hydrogen gas is 10:1. There's no cyclohexane in the feed. All species are in the gas phase. We may assume ideal gas and that delta H does not change with temperature. Okay, it says, and so it asks these questions, but they're all part of the problem, okay? But we'll follow along with its steps, because its steps follows along with how I approach a problem. So it says first, what is the equilibrium constant at the exit? What is the equilibrium composition at the exit of the second reactor? And that's really, the thing that we're getting at. Okay. What's that equilibrium? And so what I need to do in this case is I need to set up essentially two problems. Okay. Okay. And I'm actually, for the sake of time, I'm going to skip part B, C, and D. All right. We're just going to focus on part A. Okay. So I'm going to treat this as two separate problems. Okay, with the same reaction though. I have benzene plus hydrogen goes to cyclohexane. So the first thing I need to do is I need to balance my reaction. Oh, that's not right. That should be a 3. 6 plus 6 equals 12. Alright, so now I'm good. Alright, so I balanced my reaction. That's good. Okay, now what do? I make a table. Okay, and so we're going to call this species 1, we're going to call this species 2, and we're going to call this species 3. Okay, and so I have species, and I'm going to have two tables. Okay, I'm going to have two tables because I have two operating conditions. Okay, so I've got species. Okay, so we're going to have species and Ni naught plus nu I squiggly equals Ni, which is going to be the Ni naught of the other one, plus nu I, which is still the same squiggly, which is going to equal the actual Ni final. Okay, so 1, 2, 3, and then of course total. Alright, so initially it says I had a 10-to-1 feed ratio, so I have 10 moles of species 2, I got 1 mole of that, and I got nothing coming in. Alright, I've got -1, -3, and +1. So I have here 1 minus squiggly, 10 minus squiggly, 10 minus 3 squiggly, and then squiggly. And that's my initial going into the other reactor. Okay. So 1 minus squiggly, 1. So I'm going to have to distinguish these squigglies. I got first reactor and then I got the second reactor. So 1 minus squiggly 1, 10 minus 3 squiggly 1, and then squiggly 1. Minus 1 times squiggly 2, minus 3 times squiggly 2, plus 1 squiggly 2. So I've got 1 minus squiggly 1 minus squiggly 2 equals 1 minus squiggly 3, 10 minus 3 squiggly 1 minus 3 squiggly 2. And then I've got squiggly 1 plus squiggly 2. In terms of totals, I've got 11 to start with. I've got minus 2, 10 minus squiggly 2 minus 2 squiggly 1, 2 minus 2 squiggly 1, minus 2 squiggly 2 equals 11. 11 minus 2 squiggly 1 minus 2 squiggly 2. Alright. Okay. And there's my moles. Now I just need to get my K. My K is always equal to pi fugacity over fugacity reference y to the new I. Now this is the gas, so everything fugacity-wise is yip. Okay? And so I have n3 over n1 times n2 to the cubed times p to the new. In this case, my new is the same no matter what. Okay? And so my p is luckily constant, so that's kind of convenient. But my p in this case is minus 2. So I've got p squared, and I've got n total squared. Okay. And that's equal to my k, but I kind of have two k's. Okay. So I got kind of my initial and then my final, in a sense. Okay. So so basically I'm going to do the math twice. Okay. It's just that my initial is going to be 1 minus squiggly 1, not 1. Okay. And again, I'm going to have to solve for squiggly in each case. Now squiggly in this case is not exactly easy to solve for. I'm going to have to set up solver to solve this for me. Okay. But where do I get k? I have two equations for k. I've got natural log of k over k naught equals minus delta H of a reaction at standard conditions over R, 1 over T minus 1 over T naught. Okay. And then I got k naught equals exponential of minus delta G naught of reaction over RT naught. Okay. And so I can actually do some manipulation here. Now I'm going to leave my table because I kind of need my table. I'm running out of room real quick, but I'm going to try and fit this. Okay, so I've got natural log of k minus natural log of k naught. Move that over and plug that into here, and so I have, because it's my, I have positive natural log of k naught, so I have minus delta G naught of reaction over RT naught minus delta H naught of reaction over RT plus delta H of reaction naught over RT naught. Okay. All right. Yeah. And so that's a fine way to do it. Okay. Where do I get delta H reaction? Well, and delta G reaction, well, that's easy. Okay. Delta G naught of reaction is equal to summation of nu I delta G of formation of component I. And delta H naught of reaction is equal to summation nu I delta H of formation of I. And where do I get delta H of formation? From the book, okay? And I'll look it up for cyclohexane, I'll look it up for benzene. It doesn't really matter. Okay? I'll just plug in the numbers. I just have to remember to not forget hydrogen. To not forget, now, I know it's 0, but I still want to see minus 3 times 0. I still want to see minus 3 times 0. I still want to see minus 3 times 0. I'll get two values for that, I'll plug that in, and I'll get a k. But I'll get two different k's based on the two different temperatures. Okay. And then for each of those k's, so k1, I'm going to solve for squiggly. How do I solve for squiggly? Again, I'm going to set up solver and I'm going to have it solve for me. Let's see here. Am I able to solve that analytically? Let's check that. We'll check that one. But again, the math will essentially be the same thing on the other one. Okay, so N3 was squiggly 1 over 1 minus squiggly 1 times 10 minus 3 squiggly 1 cubed. Yeah, I'm thinking that cube is going to mess things up real quick. Yeah, it's going to. So I don't think I can solve this analytically. I need a computer and solver to solve this thing. To solve this thing. Okay. To solve for what the first squiggly is, and then I'll plug that in to figure out what this second squiggly is. So at that point, it's just plug and show. Now, you don't have to do part B's and C's and D's, but let's just kind of look at them. What's the purpose of the first reactor? That is, why do we use two reactors instead of just one? Well, probably depends upon the if this reaction is exothermic or endothermic. So let's just kind of eyeball that. Is this exothermic or is this endothermic? So I go to my trusty formation tables. Benzene in the gas phase is 82.98, so about 83. Cyclohexane is about minus 123. So this is highly exothermic. Highly exothermic. Okay. So a lower temperature is better to have. Okay. And so I want a lower temperature in general. Now why don't I just use 265? Well, A, there might be some kinetics associated with this, so that I want to get some of that hydrogen converted. Okay. The other thing is, okay, I convert some of this to cyclohexane. Well, now I have less products, and so there's not as much driving force. So I lower the temperature to re-increase the driving force. Okay. All right. Why would we get more product if we use the pressure of 1 bar instead of 5 bar? Well, that comes from this, ideally. Okay. Well, nu is less than 0, and so a higher P results in a higher product. All right. Would you recommend diluting the feed with an inert to increase the yield of C6H12? Well, that's an easy question too. An inert would increase this guy. 1 over an increased number means this decreases or increases. If this increased, what would this have to do? This would have to decrease. And so that would be a bad thing. Okay. So those are easy to answer.